vice versa. So I know we're all very proud people, and normally a lot of programs don't like to ask for help. So until it's very late, and they tried everything they could. So it's possibly just the threshold, so that it doesn't immediately notifies everybody on your friend list that you're having trouble. And then it allows us to pinpoint issue spots. If the whatever we're working on is failing, we can actually use Eclipse Helper to rewind to each difficulty point, and then see all the steps that we took until we had a little collapse. And then there are industrial use. One big area that difficulty prediction is pretty applicable to is API design. We have this nifty new API that we have. There are different blueprints we want to use. Which one should we use? So in order to know that, we can do a user study, and we look at how much difficulty different users have with the API, to know if each blueprint plays well with real life coding, and then it will be prudent to not actually choose the blueprint that causes the most difficulty among the users. And then educational, I know there's a lot of TAs and professors here, but so if the students are encountering a lot of difficulty in a particular assignment or section of assignments, it's pretty much hinting at maybe the difficulty level of the assignment needs to be reduced. But what's best about that is that it's easy to tell what section of the lecture that should be more elaborated on, or maybe have a little bit more recitations on a subject that people are stuck on, if students actually build the recitations. And there are many, many more. So here's a general model for difficulty detection scheme, aka the design space. We have the inputs, we have the mapper that maps all the inputs to an attribute for the classifier, and then we have the set of attributes for the classifier, and then we have the classifier, and finally we have the evaluation stage that trains the classifier and then tests on how well it performs. So you may have noticed there is a oversampling stage in here. Well, the reason for that is because, as you can see by the bar graph down at the bottom, the not stuck class is the vast majority of the inputs, while stuck is just a tiny minority. And what the classifier will do in this instance is that it will predict everything as not stuck, because Occam's razor, it can predict everything as not stuck and still get 96% overall accuracy out of it. So we need oversampling to boost the number of instances of stuck class, so that the classifier will at least consider predicting it. And that's a major source of difficulty here. So the previous implementation, this work is a direct descendant of a doctoral thesis by a PhD student here called Jason Carter, and this project inherited all the data he collected. He collected 16 participants' data, but only used 13 for that reason. So I want to take all those 16, added some additional data to it. And Jason also had a base difficulty prediction scheme in his doctoral thesis called A1J. And what A1J had is that Jason had his own mapping of the inputs to the various attributes for the classifiers. He used SMOTE to oversample the minority class too. He had a J40 tree for prediction, and then he used tenfold cross-validation for model verification. As you can see, according to cross-validation, the result is pretty good. We had a 95% overall accuracy, and there's a pretty decent accuracy for true positives. But he only explored one point in the design space. What I seek to do is explore every dimension of the design space and find the classifier that can best predict true positives, true negatives, and improve upon the great base that Jason had. So now we can talk a little bit about the mapping dimension of the design space. So for lack of better names, Jason's mapping is called A1. That's the original mapping. The current research introduces two different mappings. A2, which inherited Jason's mapping to the insertion attribute for the classifier. And it inherits insertion and delete. A3 has its own insertion mapping to insertion and delete, while both A2 and A3 introduces a new attribute for the classifier called web link, which is just the amount of time that a person uses the internet while programming. And Jason did not use web link in his. So now that we know what the events from the Eclipse logs map to the classifiers, we gotta choose the best attributes for the classifier. And there are 6 different attributes, and they're all namesakes for the various things that people do while programming. You know, if they type in code, that's insertion. If they delete code, that's deletion, etc. So basically, it's very impractical to take all the events from Eclipse and then shoot it straight to the classifier. So what we want to do is aggregate a bunch of them, you know, and then calculate the ratio of how many are inserts, how many are deletes, and then use that ratio to train a classifier. So the segment length is 60 of those Eclipse events. So get mapped to a single segment for the classifier. And then the startup lag is 25 events, so that when a person is just starting up, we don't want to collect events immediately because they might be tainted. All right, so on to oversampling. There are 2 oversampling algorithms that we'll explore. One is SMOTE, and what it does is that it generates synthetic minority class samples. And what we hope to achieve by doing this is to make the minority class space more general, which is good because we don't want it to be, since we only have 68 stuck instances, we don't want the classifier to overfit to those 68. And then resample is introduced in this research as a baseline for comparison. You know, in case that generating synthetic samples does, you know, damage the classifier accuracy, we want to test if that's actually the case. And then it doesn't generalize the minority class space. So and then we have the classifier. There are 3 major classifiers that we use: J40A3, which was in the original research, and it's been proven to be very successful at accurately predicting true negative, and a pretty good baseline. Well, the current research also introduces 2 other classifiers: AWS.M1 with decision stump, which is great at predicting hard to reach instances by training an ensemble of classifiers, each on the instances that the previous one missed. And then there's also bagging, which also has its own ensemble of classifiers, but it mainly reduces variance instead in training sample. And now we have the evaluation stage. So we have 2 evaluation methods to evaluate how well the classifiers perform. There's tenfold cross-validation, which is an industry standard, but what it does is that it kind of evens out the distribution, so that the outliers are presented in the training sample, and then the outliers are also presented in the testing sample. And then we have the one out participant validation, which is a special one we use for this research. And what it does is that it leaves all the data for different participants out. and then all the ones for in turn, and then it trains the classifier on everybody's data besides the one that's left out. So it gives, so it basically introduces an independent testing samples. And here's a summary of all the different features and the dimensions. The stars are the ones that was in the original research. So the original research was pretty good, but after testing A2 with cross-validation, there is a general improvement all across the board. A2 has 90% overall accuracy compared to A1, and then it does a lot better on the true positive predictions. However, true negative is a little bit lower, but and this potentially might be due to WebLink being introduced as an attribute in A2. So what we want to do is test whether WebLink is actually a great attribute, and it did end up being a really good attribute. We use information gain evaluation. So it ranks WebLink consistently as the top attributes. And what information gain does is that it measures, starting with a set of data, it measures how well each attribute can separate the data into pure classes, sets of classes. In this case, we start out with a bunch of data that has a label stuck and not stuck. It will test how well, like, it can separate into groups of pure and not stuck, and then pure stucks. And that is, and how we measure how pure it is a measurement called entropy. Entropy is a number between 0 and 1. 0 being that it is very pure, and then 1 being that it's a mix between all different classes, and that's the worst case scenario. So now we want to see how well do the mapping for A3 and A2 performs in cross-validation. And the result from here is that the mapping that we use at A2 is still the best one. So the summary from the cross-validation analysis is that A2 is undeniably the best scheme for predicting difficulty. But like I said before, cross-validation does kind of evens out distribution a bit. So I also want to do leave one out participant analysis to see how well the classifier can perform on independent testing sets, like just a random set from any person. And the result from that is A1 from the previous research kind of just drops off a cliff in terms of true positive. True positive, it used to be 77% with cross-validation. Now with this new analysis technique, we're getting 4%. And A2, A3 likewise also experienced a drop, but not as significant as A1. So what that tells us is that cross-validation might not be the best method to test the performance of difficulty classifiers. Yeah, so one of the early goals of the research is to find a scheme that can do best in overall, one that can do well in true positive, or better yet, one that does just good in all of them. Well, so I've seen before, A1, A2, and A3, which A40, A3, does not do very well with true positives. So AWS.M1 with decision stump was introduced since it has the best chance with hard to predict data. So we tested a scheme the schemes with ADA boost, and we found out that scheme A2 with ADA boost gives us the undeniably best true positive accuracy, which is 80%, as compared to before. The previous A1 scheme, we get only 4% of that, so it's a 20-fold increase. And A3 also does relatively well, but not as well as A2. So ADA boost.M1 with scheme A2 gives us a good true positive accuracy, while only a slight compromise on true negative prediction accuracy. So, and in terms of overall prediction accuracies, J48 still reigns supreme. 91% overall. It's 41% for true positive, and then 95% for true negative, and that's achieved with scheme A3. But as compared to before, it's definitely an improvement in terms of true positive, and it also does better in the overall accuracy department. So now I want to look at what happens. How does oversampling affect our results? Okay, so how does oversampling affect the results? And what basically happens is that, as I said before, the classifier will predict everything as true negative. And the overall accuracy is good, but true positive is really bad. And basically, as overall, as minority, the number of minority instances, class instances goes up, overall accuracy goes down. But true positive will definitely go up. And then ADA boost gives us the same story. So we compare SMOTE to resampling afterwards. SMOTE wins in all the categories: best overall accuracy, best true negative, and best true positive. So the verdict is, if you want overall accuracy, get A3 scheme with J48 and SMOTE to 30% in the majority class size will give you the best overall accuracy and the best true negative accuracy. But for true positive, you want A2, scheme A2 with ADA boost and SMOTE to 3,000% of minority class size. So conclusion, cross-validation is not necessarily indicative of real-world difficulty classifier performance. WebLink is a great attribute at discriminating between stuck and not stuck segments. SMOTE is slightly superior to resampling for boosting the prediction of the rare minority stuck classes. And as I said before, for tasks where true positive is important, such as API testing, you want to use scheme A2, ADA boost, and SMOTE, and to 3,000% of minority class. And then for real-time coding collaborations, scheme A3, J48, and SMOTE to 30% of majority class size should be used to minimize false alarm and wasting the collaborator's time. And that's it. Any questions?
Question. I have one.
Mm-hmm.
What can you intuitively tell me why weblinks turns out to be so important?
Because J48 is built on information game. It literally at each stage tests how between the different attributes, which one will be able to separate out the data in the beginning into different groups, and then how pure each group is.
So why is weblinks pure?
Why is it pure?
I'm just intuitive.
Intuitive reason. So I guess if people are having difficulty, they'll be more inclined to use websites. And you're not having difficulty, they're less inclined.
Also, the data you were testing was an API-centric problem.
Okay.
It was based on, they had to build a swing application.
Yeah.
So